Hello everyone, myself Mrs. Archana Mhatre, lecturer in Electronics and Telecommunication Department. In this video, we are going to continue with the fourth unit of Basic Electronics, that is Field Effect Transistor. So in this video, we will see the JFET biasing. The biasing is a process of applying external DC voltage of appropriate amplitudes and polarities to various terminals of FET. The biasing is essential to operate the FET in the desired region of operation such as cutoff region, saturation or ohmic region. The commonly used biasing circuits for FET are: first is fixed bias circuit, then self bias circuit, voltage divider bias circuit and source bias circuit. The region of JFET operation. In cutoff region, the JFET acts as an open switch. In saturation region, JFET acts as an amplifier, and in ohmic region, JFET acts as a closed switch. Now first, biasing is fixed bias configuration. The simplest biasing arrangement for the N-channel JFET is fixed bias configuration as shown in figure. Here you can see this is a gate terminal, drain and source terminal of FET. Here in gate terminal, the capacitor and resistor is connected. The voltage supply is given to the gate terminal. The VDD is the positive voltage given to the drain terminal, and here the output voltage will be calculated. The capacitor C1 and C2 are the coupling capacitor which are used for coupling the AC signal to the input of the circuit and amplified AC signal from the output of the circuit. However, for the DC analysis, these capacitors are equivalent to open circuit. For DC analysis, Ig is equal to 0, therefore the voltage drop across Rg, that is IgRg, is equal to 0. This will allow us to replace Rg by a short circuit for the DC analysis. The simplified fixed bias configuration used for the DC analysis is as shown in figure. Here the modification of the fixed bias configuration circuit. The general procedure that is to be followed for the DC analysis of any biasing circuit is as follows. First, to calculate VGS by applying KVL, that is Kirchhoff voltage law, to the gate circuit. Second step, to calculate ID by using the Joukes equation. And third step, calculate VDS by applying KVL to the drain loop. So step 1 is to calculate VGS. Apply KVL to the input loop or gate loop. So we will get the equation as VGS plus VGG is equal to 0. Therefore VGS is equal to minus VGG. As VGG is constant, voltage VGS also will be the constant, and therefore the name of the circuit is fixed bias circuit. Step 2 is to calculate the drain current ID. The expression for the drain current ID as per Joukes equation is as follows. ID is equal to IDSS into bracket 1 minus VGS divided by VP, the bracket square. Third step is to calculate VDS. The drain to source voltage can be obtained by applying the KVL to the output circuit. That is VDD is equal to IDRD minus VGS is equal to 0. So therefore we'll get the VDS is equal to VDD minus IDRD. Next, a biasing circuit is self-bias configuration. The self-bias configuration for FET need only one DC power supply. This is its advantage over the fixed bias circuit, as in fixed bias circuit we have seen the two power supply will be applied on a circuit. The DC analysis of the self bias circuit. For DC analysis, capacitor C1 and C2 will be considered as open circuit, and the resistor Rg will be replaced by short circuit as Ig is equal to 0. The simplified DC equivalent circuit is as shown in figure. First step is to calculate VGS. So applying KVL to the gate circuit will get equation VGS plus IDRS is equal to 0. So VGS is equal to minus IDRS. Here VGS is not a fixed voltage, but it is a function of the output current ID. Second step to calculate ID, that is drain current. The expression for the drain current ID as per Shockley's equation is as follows. ID is equal to IDSS into bracket 1 minus VGS divided by VP bracket square. Substitute the expression for VGS, we get ID is equal to IDSS into bracket 1 minus IDRS divided by VP the bracket square. Step 3 is to calculate VDS, that is voltage from drain to source. Apply KVL to the output loop. Here we will use ID is equal to IS. So we'll get the equation VDD minus IDRD minus VDS minus IDRS is equal to 0. Rearranging this equation, we'll get VDS is equal to VDD minus IDRD minus RDRS. Therefore, VDS is equal to VDD minus ID into bracket RD plus RS. Next biasing circuit is voltage divider bias. The voltage divider biasing for a JFET amplifier is shown in figure. This configuration is exactly same as the one used for the biasing the transistor, but its DC analysis will be different. In the DC analysis of this circuit, we will assume that Ig is equal to 0. The coupling capacitors C1, C2 and Cs are assumed to be open circuit for the DC analysis. In addition, the source voltage VDD is separated into two equivalent sources. The simplified voltage divider biasing circuit for DC analysis is as shown in figure. We can write IR1 is equal to IR2 because Ig is equal to 0. And IR1 is equal to IR2 is equal to VDD divided by R1 plus R2. The DC analysis of this circuit, first step is to obtain the expression for VG. VG is equal to R2 divided by R1 plus R2 into VDD. The second step to obtain the expression for VGS, applying KVL to the gate source circuit, VG minus VGS minus IDRS is equal to 0. Therefore, VGS is equal to VG minus IDRS. Then next step to obtain the expression for VDS, apply KVL to the drain circuit. So we'll get the equation as VDD is equal to IDRD plus VDS plus IDRS. So VDS is equal to VDD minus ID into bracket RD plus RS. Similarly, we can get the expression for VD as VD is equal to VDD minus IDRD. Thank you.